All right, welcome MDM4U. You are in the right place. You have clicked the right button. If you want to just copy down the note, you can do that like just copy this like you would in class, copy down, or you could print off the PDF version using your own money and printer, ink, and all that business, and then just fill in the blanks. I'll leave that up to you. The last couple of days have been talking about the binomial distribution, where we were interested in the number of successes out of a fixed number of trials. We're going to, switch the focus today a little bit and talk about what's called the geometric distribution, also called the waiting time distribution, and we'll see why it's called that in a second. But the expectation we see is just to be able to use some formulas to calculate probabilities and expected values of this new distribution that we don't know anything about yet. Let's get right into the example. An example, a researcher knows 30% of Perth County residents are smokers. And that's fairly accurate. Actually, this is slightly old data, but that's a fairly accurate number and fairly recent. If she calls 5 random numbers, what's the probability she contacts a majority of smokers? A majority of smokers. So 5 numbers, that means she wants to contact 3, 4, or all 5 are smokers. And this is just binomial, isn't it? This is binomial, where we're interested in the number of smokers that are contacted. And essentially what we want is the probability that we have a majority. And this is the advantage of our Chapter 7 notation, that we can talk about more than one case at a time. And what's that equal to? It's equal to the 3 cases that we just discussed, right? When we have 3 smokers, or 4 smokers, or 5 smokers, right? I'm just going to add them all up. Each of these calculations is one of these, and I'm going to change colors just so it doesn't get mixed up, that each one of these calculations is one of these, right? Where here n is 5 calls, x is, well, x takes 3 values, right? 3, 4, and 5. So I'm going to repeat this calculation for those 3 different values. Probability of success. Success is, well, I guess we should define that, shouldn't we? Success is contacting a smoker, right? Contact the smoker. Because then we can talk about the probability of success, right? So the probability of success, 30% of them are smokers, is 0.3. Then the probability of failure is 0.7, and just subtract that from 1. And then I'll show you an example of one of the calculations, and then you can do the rest. 5, choose 3, 0.3 to the exponent 3, 0.7 to the exponent 5 minus 3 is 2. And get my graphing calculator going here. Get out of that. And I got 5. Choose 3 times 0.3 to the exponent. There's the exponent button. 3 times 0.7. See, in class, I just wait for one of you smart, fast calculator people to put that in, and that'd be good. 0.1323, and so that's this number here. That's the 0.1323, and hopefully some of you are good at doing this on your calculator and can just go back and change the values, right? That's got to be 4, that's got to be 4, that's got to be 1, and you can change this. Excuse me, you should get these values. And this one is almost 0, almost no chance of all 5 of them being smokers. And that's a total of 0.1631. So therefore, there's a 16% chance of a majority of smokers. So that one's basically a review of yesterday. This is a binomial question, and it's kind of like a hard one from yesterday. But B, we see a slightly different type of question. What is the probability she finds the first smoker on the fourth call? So notice this is a little bit different. I'm not necessarily interested in the number of smokers. Well, it's one smoker, but it's after exactly 3 non-smokers. It's kind of like the probability, the calls have to go like this. It has to go a failure, so a non-smoker, 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 and then on the fourth call, finally we get a smoker, a success. And so, how do I get going down there? How do I gotta get rid of my bar here? Oh well. I'm just gonna wonder what's going on there. Let's just get rid of that. I bet you now it'll go. Yeah, there it goes. It went away. Good. What's the probability she finds the first smoker on the fourth call? It has to go failure, 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 success. Non smoker. Well, what's the probability the first one is a failure or a non-smoker? Well, that's 70%. The second one, well, 70%. We're assuming they're independent trials. 70%. And it has to be this way. It has to have this very, very specific form. Has to go 0.7, 0.7. And notice that if I wanted to shorten that up, it could be 0.7 to the exponent 3. There were 3 failures before this first success, and I can put that into a calculator, and I get that much. Therefore, there's a 10% chance, and this is where the idea of the waiting time, the word waiting time, she would wait until the fourth call for her first success. And this idea of waiting for a success, that's this new distribution, the geometric distribution called the waiting time distribution. So given a Bernoulli trial, the probability that the first success after X failures, so where X is the number of failures before success, not the number of successes. It's a different distribution. This is different distribution. Probability of little x failures before our first success, then would just be failure, 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 then finally failure, 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 x failures before our first success is just that little formula right there, and that's it. This is what's called the waiting time distribution. So, and the next little point is the expected number of failures before the first success, called the expected waiting time. The expected, how many calls should she expect to wait for before the first success? Well, remember from a couple of days ago when we did expected values in general, we had that formula. Well, notice that this is and you don't have to write this part down, please just listen and learn. That we had x times the probability of x. That's how we get the expected value. Notice, well, we could get 0 failures and we could get our first success, our first smoker right away. Or we could wait through 1 or 2 non-smokers before our first failure. Even though it's not very possible, we could make 100 phone calls and each of them be non-smoker before our first success. How big is this table? It could go on forever, even though it's not very likely we could make 1,000,000 calls before we get our first smoker. And this isn't very likely, but imagine trying to add up this table. This table is infinitely long. Well, luckily, we have a little formula. And the little formula is the probability of failure over the probability of success. That's it. So in this example, how many calls should she expect to make before reaching her first smoker? What's her expected waiting time? Well, 70% chance of failure, 30% chance of success, and that's about 2.33. So what does that mean? She should expect 2.3 failures before success. In layman's terms, or in this case, we'd probably expect her by the third call, she'd reach her first smoker. Okay, I'm just going to check my time and see how I'm doing. I'm going to stop it there. We'll pick it up in part 2 of the video for example 2.